Hello everybody, the topic of this video is clusters of stars. Stars are rarely formed in isolation, if ever formed in isolation. They're always born in groups of stars, and these groups can be small from a handful, a few dozen stars, all the way to these enormous star clusters that we call globular clusters, which contain hundreds of thousands to millions of stars. We have already seen a little bit of the precursors of why we see stars born into star clusters. It has to do with this triggered formation and that a single molecular cloud has enough material to form lots of different stars. And that very first stage of star formation was the fragmentation. So there's enough mass in a molecular cloud to form dozens to thousands of stars. And it's going to fragment into a smaller little bits. And each one of those fragments will form a star. So let's go ahead and take a look at star clusters. They are our ideal laboratory for studying the stars. And I have two examples over here. These are both of what we're about to see are open clusters of stars. But you can see that the emission nebula, some of the remnant stuff that the star cluster was born out of, the ISM material, the molecular cloud, and you can see all of these very bluish colored stars because we're still seeing the hot young stars, the O and B type stars. And then one of my favorite open clusters of stars, the so-called wild duck cluster. You can see that down here. And again, you're seeing lots of the O and B type stars, but there are a whole bunch of stars that are going to be smaller, fainter, and dimmer and harder to see. Because remember from the IMF that you form more low mass than high mass stars. All right, so we have our molecular cloud that has enough mass to form multiple stars. And depending on where in the universe and when in the universe you're talking about, these clouds of gas can contain dozens to hundreds of dozens to maybe a few thousands of solar masses. So you could form dozens to thousands of stars, but some of them could possibly form up to hundreds of thousands of stars, giving birth to things that we call globular clusters. So, in short, through this sort of triggered formation through shock waves that can set up these chain reactions, and the fact that we have a whole lot of mass in a molecular cloud with all of these different dense clumps, we get stars that form in clusters, which is a really powerful thing whenever we want to go and study the stars. Because they formed out of the same molecular cloud, then they formed all at the same time, so they have the same age, they formed in the same place, so they have the same distance away from the Earth. So at that point, just looking and seeing, hey, in that cluster star, that star is brighter than that star, is saying something about their absolute brightness since they're all the same distance away. And they have the same overall composition. Not all molecular clouds have the exact same composition, what we call metallicity, the total amount of elements heavier than hydrogen and helium in there. But a star cluster, all the stars have the same composition because they're formed out of the same cloud. So that's a lot of the same going on with the cloud that these star clusters form out of, which means that the stars themselves are going to be tightly constrained in their initial properties, their composition, their age, and we can leverage easy things like they're all a convenient similar distance away. They're all in the same place in space. So star clusters become our ideal laboratory. They have the same environment that they're forming out of. They're made out of the same stuff. They all have the same age. So if we want to go ahead and look at the properties of stars and have the best possible set of data to look at, we choose star clusters because they're a very well controlled sample. So often you'll hear people refer to star clusters as the ideal laboratory for studying stars. And this can be everything from just the properties of the stars themselves to how stars form. So formation scenarios, what that entire Hayashi track sort of idea, to studying how they live on the main sequence, to studying how they evolve off the main sequence and die. We want to study star clusters so we can study stars in detail. And we have two types of clusters of stars, or two primary types of clusters of stars. We have the so-called open clusters, and these are what is said to be gravitationally loosely bound. And they contain up to a few thousand stars, sometimes only a few hundred, sometimes only a couple of dozen stars. And since there's so few stars there, that means that there's not a whole lot of gravity from all of the stars that are there, which means that yes, while that's a large number of stars, I mean, think about hundreds of stars or thousands of stars, sounds pretty massive to me. There, with the distances between them, there's just not enough gravity to keep them orbiting all one another. So over time, they will drift away from one another. And so they will no longer be a cluster. In fact, our sun was almost certainly born in a star cluster. And there are some people out there who are dedicating much of their careers to try to find our stellar siblings, the the stars that were in the cluster that we were formed out of roughly about 5 billion years ago. A hard task to do since all the stars have drifted away from one another. So when we say gravitationally loosely bound, right now they're all very close to one another and gravitationally influencing one another. Well, over about 100 million years or so, or a few hundred million years to a billion years, they'll drift apart. There's not enough gravity to hold this thing together. So open clusters have fewer stars and they're young. Since are gravitationally loosely bound and will eventually drift away, for all the stars will drift away from one another. If we see one, it's got to be pretty young. And typical ages are tens to hundreds of millions of years old. That's getting it back to like the age of the dinosaurs or so, 65 million years ago, or when the dinosaurs went extinct. So these are cosmically young, which is really great because if we want to study the high mass end of the initial mass function, we want to study the O and B type stars. Where are we going to find them? In star clusters, the youngest star clusters, because they will still have their O and B type stars. They haven't burnt through all of their hydrogen, fusing into helium, and then going to death throes and exploding in a supernova. We can still observe that. So the Milky Way is still actively forming new open clusters of stars, quite a few actually. If you look at the spiral arms, they are always pictured to be blue because you're actually seeing where the star formation is happening. You are actually seeing where the clusters are being born out of molecular clouds. The second type are monstrously large. So the second type of cluster are globular clusters, and these are gravitationally tightly bound, which means that there are so many stars there, hundreds of thousands to millions of them, where they have enough gravity as a collection of stars to keep that cluster together. It won't drift apart over time. And because gravity is what's tightly bounding them together, they settle into a spherical shape. So they don't have organized orbits. They're sort of like buzzing around, but roughly circular-ish orbits. But they end up having this spherical shape, and they are clusters of hundreds of thousands to millions of stars. So the most massive one in the Milky Way galaxy is called the Omega Centauri globular cluster, pictured here. From edge to edge, the diameter of this cluster is only 172 light years compared to, say, I want to flip back for a second. That our open cluster was 13 light years, so an order of magnitude larger, but we are packing in hundreds of thousands to millions of stars in this really, really tight confined space. One of the things I always like to imagine, and it blows my mind every time I stop and think about it too much, is imagine that around one of these hundreds of thousands, or really is about 10 million stars for the Omega Centauri globular cluster, you find a planet that's habitable. And imagine yourself on this habitable world, laying out, looking up at the night sky, and you have 10 million stars crammed in 172 light years. Our nearest neighboring star is 4 light years away. There'd be so many stars in the sky that night might be as bright as day. Instead of seeing thousands of stars in the sky, there would be hundreds of thousands of stars you could see in the sky. That would be incredibly strange. And another example, one of the more famous ones, Messier Object 13, M13, also called the Hercules globular cluster. It's about the same size, but this one only has a couple 100,000 stars. But I wanted to include this one because you can zoom in and you can see that you have reddish stars, older evolved stars. You still have some stars that are kind of bluish in color. But in general, globular clusters, or at least the Milky Way globular clusters, because the Milky Way is no longer forming new globular clusters, globular clusters are old, like really, really old. The average age for the globular clusters of the Milky Way galaxy, they range between 10 to about 13 billion years old. That pushes them to be about as old as the universe itself. So as soon as galaxies started to come together and stars started to be formed, that's whenever the Milky Way's globular clusters were being built. So it's rare to find ones that are much older than, say, 12-ish billion years old. But I have the ages for these two over here. And notice that one of them is 11.5 and the other one's 11.65 billion years old. And we don't seem to be forming any new globular clusters, but we see galaxies out there that are in vigorous stages of star formation. They're forming lots and lots and lots of stars currently, so-called starburst galaxies, and we see that globular clusters are forming there. So yes, they they do form. The specifics on how globular clusters form are not fully understood. All right, and I want to give you just a little bit more about globular clusters. I want to really hammer in why they're ideal laboratories, and a lot of this comes back to, okay, if they're ideal laboratories, they all have nicely, tightly constrained properties. The HR diagrams that looks at stellar properties of these things should be really interesting. That's how we really go about studying stars. We refer back to the HR diagram. So star clusters and HR diagrams should be two things that go really well together, and they do. I'm just going to go ahead and introduce this star cluster right here. It's another open cluster of stars, perhaps the most famous one. You have maybe even heard of it and probably mistaken it for the Little Dipper before, but it's not the Little Dipper. It is the Pleiades star cluster. It's viewable naked eye, so it's pretty easy to see near Cassiopeia. And you can, it's also known as the Seven Sisters, or if you're in Japan, it's not called the Pleiades, it's called Subaru. And if you ever look at a car, a Subaru car, and look at the symbol of a Subaru, it's a collection of stars that are roughly in this pattern right here. Ah, that's where Subaru got their symbol from. It literally is this star cluster. So it's the Pleiades cluster. It's a fairly young cluster. It's only about 100 million years old. It has over 1,000 stars in it. It's really close cosmically, only 130 parsecs away. And given its age, it still has B-type stars, which you're seeing right here. The Seven Sisters, of which naked eye, you can only see 6 anymore. Okay, so I just want to introduce the Pleiades cluster because it's really fun and exciting. And it's something you can walk outside on a clear night and see with your naked eye. But let's go back to star clusters being ideal stellar laboratories. And I can't hammer this part in enough of why astronomers love star clusters, other than they're really cool objects in a telescope, naked eye, or with a small telescope. But we are dealing with a controlled population of stars. They're all the same age, the same composition, and the same distance away, and they formed in the same sorts of environments. So all the external factors are well controlled. We're always trying to control as many of the variables as possible in a science lab. And here's a natural science lab in outer space that's controlling a lot of the variables of stars. Which means that when we look at our models of stars, of how we form stars, how they live in the main sequence, and then how they evolve off the main sequence and die, our stellar evolutionary models, we have those things based off the standard solar model, then we want to compare those models and our theories about how stars work to star clusters, which are a very controlled population of stars. So it's a direct way for us to compare properties of the stars, test our models, explore things like the initial mass function. And this one, we've only lost the O stars, but we can sample the rest of the initial mass function. And it's going to really give us a way to study the details of stellar birth, life, and death. And you can start to see that it's going to be a topic for another video where we talk about stellar evolution. But I wanted to go ahead and show you some of the main sequence for the Pleiades, really the HR diagram for the Pleiades cluster. So right here, almost all the stars are in the main sequence. You still have B stars. The O stars have started to evolve off the main sequence. They've gone past their main sequence stage where they're fusing hydrogen into helium in their cores, and they're evolving towards death. They're going to make their way this way on the HR diagram, do a couple of waggles back and forth, and then explode into supernova. And then you can see the main sequence. And you can even see there's this weird upturn kind of in the M region at 100 million years old. The M stars haven't finished their protoplanetary phases. So we're seeing the very tail end of the formation of the M stars while we're watching the O stars die, the O and B stars die. And we're only looking at the main sequence, and every one of these stars has the same composition. So this is a very controlled population of stars. Notice that you can't see anything in the red giant region. You don't see any white dwarfs because they don't exist for the star cluster. Now let's compare that to the HR diagram of a globular cluster. So this is Omega Centauri, that one that has about 10 million stars or so. And let's look at an HR diagram of these incredibly old, ancient, this one's just shy of 12 billion years old, so about 11.5 billion years old, about the time where a G-type star would be leaving the main, it would be leaving the main sequence, and we can see that the G-type stars are leaving the main sequence there. And in this HR diagram, all the high mass stars, the O, B, A, F, and now the Gs, have left the main sequence already. They've already evolved and they're heading towards death or have already died. Which means that, one, if we understand how stars live on the main sequence, we can use where this main sequence turnoff, as we call it, where you turn off the main sequence, we can use that to date the age of this. This is how we determine the age of globular clusters. These all formed out of the same group of gas and dust. So they all have the same properties. So what we're seeing here is how stars evolve towards death along the main sequence. We're seeing the pieces of the evolutionary tracks of star evolution towards death, where they're leaving the main sequence in the so-called subgiant branch. They ascend the giant branch, and then something happens and you create this horizontal branch, and then from the horizontal branch they go up the asymptotic giant branch. So these are perfect for studying how stars die, so-called post-main sequence evolution, or usually just the evolution of stars. All right, so star clusters are super cool. Hopefully you enjoyed all the pretty pictures and you learned something too. I will see you in the next video.